Okay, ladies and gentlemen, good morning. So I was just trying to check an application which is quite nice, especially for the students. This is an interactive way to look at life history, Earth history through time. But we have some problems here. Maybe the Wi-Fi is a little bit too slow in order to get really in order to get this these things functioning. Okay, so today we will be quite busy with the end Cretaceous mass extinction, and in fact for the next talk we'll see a little bit more. We'll be a little more closer from India, because I will show you quite a lot of data results coming from India. So the purpose of my talk today is to talk about one of the most known mass extinction, due to the fact that, as you know, dinosaurs got extinct 66 million years ago during these events. And I like to start that presentation with this very nice painting from Salvador Dali, which is a Spanish, very well-known painter. He was living some 20, 30 years ago. And Salvador Dali paints these very nice things here, which is a good start a little bit, because as you will see, it's a question, these things, the name of these things mean persistence of memory or time. And here I like these things because you have a little bit of everything about mass extinction. the lava flow from the Deccan traps, and more or less extinction here, and more or less it was warm, as you can see, warm and probably not very good for the biosphere if you consider that tree, and especially it's an illustration of the timing. And as you will see, time is really important in this case in order to understand better this mass extinction. So that's why I like to start with this very nice painting from Salvador Dali. It was a surrealistic painter from Spain. Okay, now what I have to say also, you will see that there will be two sides of that presentation. We'll, after an introduction, we'll speak a little bit about meteorite impact, and this is one of the trigger. And after we'll speak about the Deccan traps, mainly the Deccan traps would be also one of the trigger. And what I have to say here, in this first slide, this is a collaborator which mainly collaborate in our first phase of our work, because I started to work on the KT boundary around 93, 94, quite a long time ago, and since we never stopped to work on that. And this is a collaborator which have worked in the first time, especially about meteorite impact, for example. And here you can see that we have a multiple collaboration from multiple lands, and this is really, really important to have that, because in fact you cannot do such investigation alone. This is impossible. This is just too much work, and you need really a multi-proxy approach, a multidisciplinary approach, using any kind of geological tool like biostratigraphy, geochemistry, mineralogy, micropaleontology, a lot of things like that, which you have to put together in order to understand this kind of mass extinction. And this things is really valid for all the multi-proxy approach that you have to use. You really need to have a panel of tools in order to get a better idea of what happens during this mass extinction event. And here, these are collaborators mainly which have worked on the meteorite impact. I will discuss this later on. But we have people from Egypt, people from Israel, people from Germany, from Spain. And here one of my best friend and collaborator, Gerta Keller. And well, in the second time, we had also a lot of collaboration with Indian worker, because this has before this was more or less a meteorite team, if you want. And here I can present you the Deccan team, if you want. And you can recognize here Syed and with these big guys from USA. These guys from USA play a very important role because these are the team which are measuring the zircon in order to get the very nice age and the proof that Deccan really was one trigger of the mass extinction. Because without these guys it would have been impossible. But especially if we have all this data by now, this is really thanks to that guy here, Saeed Kadri. And I really want to thank him for all the help that he provided us since many years, because I think without his huge knowledge about the Deccan, about the age of lava flow, the mapping of the lava flow, it would have been just not possible to get all this publication, and remind you that we have 2 publications in Science about that topic. So Deccan traps is by now very well known, and here I think SciAD is really very important in that aspect. And we have also a lot of collaboration with some other Indian colleagues, but also with some PhD students. Here, Hassan Kozem, here Brian Gertsch, and many people have been worked also in India about that. So just to show you that this is really a collaborative work. By now, you cannot do all this work without collaboration, because you cannot really be a specialist of zircon datings and a micropaleontologist. You cannot know everything in geology. This is a too complex science. Okay, so after that, well, we are just moving up in time, and now we are somewhere here. As you can see, here we are somewhere here at the KPG. Okay, sometimes I will tell KT for Cretaceous Tertiary, but this is not correct, because really the time equivalent for the Cretaceous would be the Paleogene. So that's why we said Cretaceous Paleogene boundary, but doesn't really matter. But the last stage, and we use this name quite several times, the last stage of the Cretaceous is the Maastrichtian. This came from a town in Maastricht in Holland, Europe, and the Dian here, with this name Dian, come from Denmark, okay? So these are the Dian is the first stage of the early Paleogene. So you will see this name several times on all the slides. And here you can see that for the first time, we have a coincidence between at least one impact. We'll go back to that story later on, because this is, as you will see, this is quite controversial still. There is an impact, the KT boundary, but the question is to know if maybe we had several impacts or just one single. I will come back to that later. And here, a huge volcanic activity that everybody knows here, because you are living on Deccan basalt. Here, Amrati is very close to these flows. And it corresponds also to a change in sea level here. But there is no black shell deposition. Remember, yesterday and 2 days ago, we were almost always, relating black shell anoxic condition with mass extinction. In the case of the Cretaceous time, it was not the case, because very probably it was not possible due to the fact that, as I already said, the end of the Maastrichtian is characterized by a cooling leading to some ice caps on Antarctica. And these things promoted more dynamic current on the ocean. So the ocean was not like the one that we had during the Cenomanian Turonian that we have seen yesterday afternoon, but a lot more dynamic, some kind of thermohaline circulation, or some kind of, not the one that we know actually, but meaning that circulation was dynamic, so this probably inhibits the formation of black shell, which could have been the case if the ocean would have been more stagnant. And just to see here, tomorrow we will discuss about the last potential one or future one. This is the Anthropocene one. So this is just a slide that I will show you also tomorrow. We are studying this kind of event. Here this is KT boundary that you can recognize, because you have the Deccan, a meteorite, and you can see that this poor dinosaur will die off. And here this is a PTM, the Paleocene-Centaumal maximum, that we will see maybe this afternoon or at least tomorrow morning. And this kind of comparison may be very useful in order to see a little bit what happens to the Anthropocene and this very nice warming that you can see on this, for example, cloth evolutions, okay, through time. This is a joke, evidently. Why the meteorite impact is so popular? Because, well, everybody knows what is a dinosaur. Every child knows what is a dinosaur. And if you ask to many people, they will always say, yeah, the dinosaur more or less got extinct due to a huge meteorite. And since there is a lot of books, films about dinosaurs and all these things, and there is, for example, here this very nice pictures, cartoon from Gary Larson explaining that the dinosaur got extinct because they were smoking too much. Okay? And so it just means that it's very popular. So popular that every TV show, every journalist are taking this history and trying to make some kind of very spectacular but very simple explanation. And you know, journalists are, well, useful in order to get news, but sometimes they are, what I would say, a little bit limited. They are not really scientists, so they like simple story, very simple story. And clearly, the meteorite impact is a very simple story. You got an impact on Earth, and every life was just destroyed like if it was an atomic war, okay? So I think it's quite important to understand that the meteorite impact, it's a very simple story. And what I want to give you as take-home message is that this is not a simple story, by far not. And in fact, this is a multi-causal scenario. There is not a single cause, like that one, like you can see. This is this kind of picture that even Donald Trump may understand. He is stupid, but he can understand that, for sure. Well, what I just want to show you that this is a question on multi-causal scenario, which especially involve evidently one or several impact, or here especially volcanism. And this volcanism is actually located on the Deccan Traps and leads to change, for example, in climatic fluctuation. And this is more or less a take-home message that you have to take with you, especially for this week. There is no simple explanation. Unfortunately, the Earth biosphere is a very complex system with a lot of interaction. I think you understood yesterday and the last days that this interaction sometimes are very complicated. And you know, humans like to simplify. They like the simple things because it's more easy to survive with simple things, and you don't have to think. You just have to see very simple image like that one, which is probably not really true. They don't have danger like that, actually. In terms of calculation, probability calculation, there is, I don't remember, but I think this is several millions chance that we don't have any impact in the next 2 or 3 million years. So this is not a question for us, okay? Okay, so now let's go to see a little bit the story about the Kitty boundary. I will try to follow a little bit the arrow of time, starting for the beginning, the discovery of the radium anomaly and the launch of the meteorite hypothesis. Because, you know, there is some excellent books in physics, I don't remember the name, written by some American explaining that, well, when you put first a new hypothesis, a meteorite, and after, more or less, this hypothesis is so simple, so popular, that everybody is taking it, And all the people which are more or less not against, just are thinking that maybe it could be something different, are generally rejected. And when I said rejected, Alvarez, more or less the guy who discovered this iridium anomaly in Italy, proving that there was a meteorite, really destroys the careers of many, many scientists, which, for example, like MacLean was arguing a long time ago that Deccan was also responsible for mass extinction. So here, there is a big mix between personalities of people, politics, money, because clearly this hypothesis lead to a lot of very good scientific work which get funded, so it's also a question of money, clearly. And I will start from the beginning I will just show you that, I think, at the very, very beginning this week. And this is a GSSP official definition of the GSSP, which is located in Tunisia, North Africa. Although it's not like in China where they do a monument, museum, and so on. Here, well, it's you have to dig, you have to look. There is strictly no indication, but anyway, the boundary is here, and you can see that there is not, in terms of outcrops, you don't see any change, and the boundary is marked by very thin clay layers, yellow, because this is a weathered clay. And this clay contains some cosmic materials, like iridium or tektites and things like that. I will go back to that later on. And what you can see here, it's, for me, a perfect GSSP, really perfect, because here you can use several markers in order to define the base of the Danian stage, the first stage of the tertiary that you have somewhere, if this thing is working. Ooh, yeah. That you have here, okay? And what you see here, that there is a huge decrease in calcium carbonate. There is a huge decrease in delta C13. So by now, you must be able to tell me why. What would be more or less the cause of this drop in carbonate? We are in some quite deep section, open hemipelagic section. Why the delta C13 is going down, and at the same time as the carbonate are going down? Any idea? It's too early. Okay, in this kind of sediments, to what correspond carbonate? Microplankton, exactly, planktonic foraminifera. And here the planktonic foraminifera are, well, first, which is an important thing, here are declining before the boundary, but have a crash at the boundary and are replaced by some other ones. These are the Cretaceous one, big ones. As I said, I think 2 days ago, they are very specialized, adapted to warm tropical waters, and this one has the new incomers, which are smaller, they are dwarfed, and these ones are more or less used to any kind of condition, from cool to warm, and they are more or less opportunistic species. And well, you have this crash in productivity, and this crash in productivity is marked by this delta C13 shift. And here, this is a iridium anomaly. I will go back to that quite quickly. And the presence of spinel, which are minerals which are quite rare on Earth, which are probably coming from the meteorite, bolide. And you have this change in micropaleontology. So that's why I say this is one of the best GSSP, because you have chemical markers and micropaleontological markers which are coinciding on a less than 1 centimeters layer. So it's a really nice place to put the boundary between the Mesozoic, the secondary era, with the tertiary era, 66 million years ago. Okay, but we see that crash in productivity, but not everywhere. You will see that, in fact, there is a selectivity, a geographic selectivity of this crisis. Here we work in 2005, if I remember, maybe before, in Kazakhstan. Kazakhstan is located in higher latitude than Tunisia, North Africa, and this was part of the former Soviet Union. This record show very nice choke here for the maestration. As you can see here, this is this whitish things here. And you see that very dark here layer. This is a KT boundary. And on top you have more litified choke. And in this place, in fact, you don't see. We measure delta C13. This is the section here. This is a KT boundary in red. This is a red line. And you can see here that we measure directly on some foraminifera in order to have a better record, less overprinted by the diagenesis. We are measuring stable isotope, the delta C13 on foraminifera. There is no drop, no crash in productivity. It means that in higher latitude, where the conditions were cooler, more fluctuating, the fauna was already pre-adapted to this change and didn't really register a huge mass extinction. So this is quite important. And you have also to note that among the foraminifera, there is something which is very important. The crash in foraminifera is occurring amongst the planktonic foraminifera, okay? This one is not in the book. I just put it last night. So, in fact, it means that there is a selectivity also, biological selectivity. The planktonic foraminifera and the planktonic, the phytoplankton, were really affected by the crisis. There is really a drop here. But the benthic fauna, the foraminifera living on the seafloor, were almost not affected by this kind of extinction. So it means that this was mainly a problem of, let's say, the upper part of the ocean, the surface water. So it means that let's say the bad causes was coming from the sky, okay? Whatever it's a meteorite, whatever it's volcanism, it was not coming from deep ocean, because the deep ocean was not really affected. And you will see tomorrow that for the PTM it's exactly the contrary. The stress is coming from the deep ocean. I will not explain why now. Whereas the stress here is coming from the surface and from the land and from the sky. Okay? This is a big difference. So the take-home message here is to say, okay, animals like dinosaur or foreign planktonic, dinosaur living on Earth, on the continent, and the vegetation and the planktonic foraminifera, the phytoplankton surface will suffer a lot, but not really as one living in deeper water. Okay, so I already told you that the Cretaceous Paleogene boundary has been discovered a long time ago by Cuvier. That's to say at least 300 years ago. He was able to see that in the Cretaceous you have a fauna, typical fauna, which has been totally replaced by a completely different fauna. And he was more or less thinking that there was a huge event, but didn't know exactly what. That's why this Cretaceous Paleogene boundary is definitely defined, paleontologically defined, long time ago. But since '83, the explanation was quite difficult. Since really a discovery, which was one, for the geology at least, of the big discovery of the last century, and this discovery has been done by a team where you have two members of the same family, Walter Alvarez, the father, Luis Alvarez, the son. Walter Alvarez was very well known because he got the Nobel Prize in physics. So he was not really a geologist. After this helped maybe to understand a little bit why this guy was was really a bad guy. I will tell you why after. His son, Walter, was a little bit living in the shade of his father, which was very well known. You know that his father was responsible for the program of the atomic bombing over Japan, the fabrication of the bomb. And this guy was quite clever, but a very strong, dominant character. So he had the tendency to eliminate all the specialists we were not thinking as he was thinking, as you will see later. Okay, this guy, this team, and I don't have to forget another member of the team, which was very important, the Swiss guy, an English guy working at ETH, Zurich, Switzerland. He was doing paleomag. And in fact, they found this theory, this hypothesis about the meteorite by accident. It was not the purpose of the study. What we wanted to do is to measure the iridium that you have here, okay, along the Cretaceous Tertiary boundary, well below, well above, in Italy, where you have pelagic sediments, quite deep sediments. The paleo environment were at least 1,000 meters deep, so very nice pelagic limestones, full of planktic foraminifera and nanofossils, and they just crossed that boundary because they were the hypothesis, the working hypothesis at the beginning was to say, okay, iridium is coming from cosmic dust, and iridium, it's a PGE, an element from the platinum group, like palladium, platinum, iridium, and so on, is falling on Earth regularly, okay? Always, day and night, but a very tiny amount. And they were saying, okay, if from time to time we have more iridium in the rocks, it means that the sedimentation rates, the accumulation of sediment was slow, was small. If the iridium was fast and big. And if you have an anomaly, an increase in iridium, it means that the sediment was condensate, meaning that the accumulation rate of the sediments was very slow. And they wanted to use that in order, well, to define more or less the accumulation rate of sediments in this kind of pelagic sediments that you have here. And at the surprise, they cross the boundary, and this is a clay layer, and they found a huge accumulation here. But here it's not a question of sed rate or sedimentation rate, because here you start from almost 0 to 8, and these are ppb, part by billions, which is not so much, but it's so much huge increase that they know that this boundary was corresponding to the disappearance of ammonites, dinosaurs, and so on. So they put together this theory about the extinction of dinosaur linked to a huge meteorite, okay? Because iridium is a cosmic elements coming, for example, from the meteorite. But you know that the meteorite has a composition which is quite close from the deep rock of the mantle, like the basalt. We have iridium in basalt, but very tiny amount compared to this huge amount that they found. And here this is of insection, because after, when they found that, they start really to work on that. And they start to examine these clay layers that you have here. And this is the clay layers, and you see here you have big foraminifera, very specialized, living in warm tropical water. This is a low latitude place. This is in Italy, Gubbio. And suddenly there is nothing here. It's a clay layers, there is nothing left. And on top you can see reappearing small tiny foraminifera, which are more, let's say, opportunistic, less specialized, able to survive in let's say, under quite stress. And after they were looking on the component of these clay layers. And here, interestingly, they found several things. They found quartz chalk. And you can see that this is a grain of quartz with different planar deformation, with different orientation. This kind of deformation, you can get it only if you have a big shock, okay? And we know this same quartz, for example, in the place in Arizona where they were making more or less the attempt exploding the atomic bomb, doing all this essay, okay? So it means that you need megapascal of pressure in order to get these things here, okay? So this is quite important to note that we have here really the proof that there was a huge pressure, and it was clearly coming from a meteorite impact. And Syed told me that there is an crater impact here. I don't know if it is quite, I don't remember the name, but it is quite close from here. Yes, yes. Do we have shock quartz in these things? Breccia or things like that with shock quartz? Some people have looked? No. Huh? Yeah, I don't know. There is also some other things here that you cannot really found in Gubbio because, as you will see, it's too far from the crater. These are the tektites. Tektites are these very small glass drops that you have here, which are more or less linked to the collision of the bolide on Earth. And this bolide is vaporizing all the rocks down to the basement. It's an all of at least 5 to 7 meters. And if you do that, you vaporize all these rocks, and you eject these rocks into the stratosphere. And after, this drop of liquid are more and more solid. These are some glass, and are redistributed all around the impact. And more or less the distribution is all over 2,000 or 3,000 kilometers around the impact, as you will see. Iridium can be distributed all around the world because iridium will travel through the stratosphere for at least 1, 2, or 3 years, and can be, as you will see on the map, redistributed almost everywhere. So these little drops are really coming from the impact, but you don't find these things in Gubbio because Gubbio was too far from the crater. And in Gubbio and some other place, you can find this. This is an electronic microscopy pictures. You can find these very nice spinels, which are enriched in nickel, very typical for meteorite. And especially the oxygen composition of these spinels are proving that they cross the atmosphere because they are more enriched than the normal spinels that you can find in a meteorite or in very deep rocks from the mantle. Okay, so clearly all these things make the people think, wow, this was a huge impact, and effectively you can find this iridium anomaly in a lot of this section. Okay, but sometimes people were a little bit exaggerating. We can talk about an anomaly in iridium if you have at least 2, 3 to the maximum of the anomaly is in Denmark, 12 ppb, and in India, in Meghalaya. In Meghalaya, you have an anomaly, I will show you that later on, of 12 ppb, which is a lot more than in Gubbio, for example. So it just means that this iridium anomaly is really distributed all over the world. But sometimes people are using anomaly, very small anomaly like PPT, and here I think it's not very serious. Okay. Okay, so people since '83, you have a very nice publication in Nature, or science, I don't remember, by the Alvarez team. Walter Alvarez and Luis were from Berkeley University. And during this time, from 83 to 80, let's say 93, 94, I can tell you that everybody was in the, if I can use that expression, the bandwagon of the impact theory. And some people were saying, hey, but there is something else happening during this time. You have the Deccan, for example, David MacLean, who was an American, and the career of these people has been completely destroyed by the team of Alvarez and the team of Berkeley. Because during this time, you know, it was a so nice theory, it was not possible really to be an opponent. And I can tell you, in order to rise the hypothesis of the Deccan, it took almost 15 years, maybe more, okay? So I think it's important to see that when you start a so nice hypothesis, there is a period where everybody is believing it. And after, gradually, you have more and more scientists who say, yeah, but you know, it's like when you have a new methods in geology. At the beginning, the new methods, you are really in love with that. And you think that everything is working, like stable isotopes, like the temperature with stable isotopes. At the very beginning, every people will say, oh, it's really fantastic. We can see the warming and cooling by just measuring, for example, stable isotopes on foraminifera. And gradually, people more or less were aware that there is some problems, technical problems. For example, if you have freshwater input, it's the same signature that the warming. So what it is, it's difficult. You need really to know if you have freshwater input or not. Could be a variation in salinity. So there is a lot of things that are unknown at the beginning. So it's a perfect methods, but more and more there is some limitation. I will show you that with a new method that we have used in order to think more or less a tracer of the Deccan all over the world, the mercury, which was a perfect method 5 years ago, and now you can see that there is some limitation. But it doesn't mean that this method is not working. It just means, as a good scientist, you have to be aware of the limitation of all the methods that you are using. You have to be critical. And you don't have to agree with everything. Be really critical, because you don't have to be too much critical, because too much critics is killing the criticism, okay? But you really have to think about all what you are doing. And here, the story of this impact is very clear. For 10 years, everybody, and especially because it was a very simple theory, that you can do movies, you can send this to the journalists, well, understand everything. And I can tell you when we discover all these things about the crucial role of the Deccan in the mass extinction, thanks to the dating that we got, that I will explain you later on, I can tell you that if you have to explain that to a journalist, it's a lot more complicated. And if you say to a journalist, okay, well, there is a big impact on Earth, everything will destroy, you have a nuclear winter, and so on, he can understand the story. Trump can understand it without any problem. And but if you say, oh, yes, there was a meteorite, but it's more complicated because there was some volcanism, and after you have to talk about feedback, and the journalists say, what? What is a feedback, for example? They don't know that, you know. And by this way, it's very funny when we got the first paper in Science. We had a prime time on the Swiss TV at 8 o'clock in the evening, it's general information, and the guy was, wow, I have 4 minutes to explain that. It will be very difficult. Meteorite, in 30 seconds I can do it, there is no problem. So sometimes media are not really helping us, because media like simple things, and more, and I think it's really bad things. Okay, now if we follow more or less that history of the KT boundary, since this discovery, it was quite clear that you have to look for a crater, because here we have a proof. It's like the dino track. You know that there is a dinosaur, but you don't see any skeleton, okay? So until you find a skeleton, well, you have some doubts. And here it's the same. Until you find a crater, an impact crater, you have some doubts. You have some proof, but you have the iridium everywhere, for example. You have the tektite. You have all these things, but, well, no crater. So they were looking for a crater, desperately. And for 10 years, it was quite funny to see several times in Nature or Science, wow, they discover a crater, but each time the crater was too young or too old. Okay, since 90, I think it was 93. So you know that there is an interesting thing that this is distribution of the spherules here. As you can see, the people were finding spherules all over here, Central America, Mexico, North America, something like that. And this tektite were not found in Italia, but there is also some iridium. So they were thinking, maybe this impact is close by. So they go through literature and things, and they find in Mexico, in Yucatan, this is a carbonate platform, structures here, which is circular, and you can see some ring. This is a gravimetric geophysics studies, showing some ring, and here this is a seismic lines, and you can see clearly there is a hole here with at least 2 rings. And these things at the beginning was more than 12 to 15 diameter, because you need big things in order to explain big phenomena. But by now we know that it's something which was probably 120, 130 kilometers in diameter, not so big. But interestingly, you know, that place in Mexico was, you know, in Mexico there is a lot of petroleum, so there is a lot of drill core. And in way before, they were looking at some cores which has been taken somewhere here. And this is an example of this cores. And we found here a breccia, some kind of breccia with some melting and so on. At the beginning, the geologist was saying, oh, it's a volcano. But a volcano in Yucatan, which is completely a flat carbonate platform, this is something very difficult to think about. Because the difficulty here is that structures here is actually completely covered by a flat conformable carbonate platform of tertiary age. You don't have any outcrops. This is all due to geophysics and drill core, okay? But there is that breccia. So, well, another paper in Nature, clearly, yes, we found the crater, and now it's clearly the crater corresponding to the KPG impact. And now a lot of very nice story, and all of them, I don't believe that, were published about that, clearly. And this is the scenario which is proposed by people who really true, like you are believing in God, in fact, not in science, but the impact did everything. And this is in French, but I think you can understand the cartoon. So this is Mexico. And here this is the place where you find this tektite, this glass, melted glass impact coming from the impact, okay, which has been after ejected all over here and below also. In Yucatan, this is a place where you have the crater. So I just show you the seismic lines, and where you have the core with the melt basement here. So clearly it's a crater. There is no way it's nothing else. And here there is some outcrops which has been interpreted by as a tsunami sediments, meaning giant wave going back and forth and back, on and back, due to that. You know perfectly what is a tsunami in India. You had a terrific one some years ago linked to an earthquake. So this is the same thing, but you have to see that people were calculating a really giant wave. And they think that there was some sediments here containing the KPG boundary, which were interpreted as tsunami. That's to say, that have been deposited in a few minutes or few hours, maximum 1 or 2 days. So at this time, I was personally in Mexico because after my PhD that I did in between France and Switzerland about lower Cretaceous, nothing to do with the KPG boundary, I was in Mexico working in the Petroleum Institute of Investigation as a postdoc, and then after I moved to a university which was here in North Mexico, and for 2 years, and I had a fellowship for Switzerland. It was a very nice time because during winter I was in Mexico doing fieldwork and working, teaching in university, and during winter, and during the summer I was doing my labs in Switzerland. So I have already very nice weather for at least 3-4 years. And I was, and here, after 93, after the discovery of this crater, some people asked us to just to show some, let's say, some of these sediments. And here, I think there is a huge difference. People believing or working in impact are not really geologists. So they ask us to take them on the field, and in order to see these outcrops, and after we have worked a lot on these outcrops with students, I will show you the data. And clearly these guys didn't look at stones because they are not geologists. They are astrophysicists and things like that. And they say, oh, from 100 meters, it's a tsunami. Okay, we can go back to the restaurant. And after came a group from Princeton, headed by Gerta Keller. And here people were looking at sediments. And they say, oh, it's maybe a more complicated story than just a simple tsunami. So we start to investigate these things for many years. And this was before to start with the Deccan. And I will show you some of the data here. And I can tell you this is quite controversial, as you will see. So here, the scenario, I just remind you the scenario. This is an impact on Chicxulub, Yucatan. And after 1-2 minutes, you have the deposition of spheral layers here. These are this glass, which has been ejected. This is the ejecta layer, which is at the base of these rocks. And the rest has been interpreted as a tsunami, as you will see, which I really don't believe for many reasons that I will explain now. And this is the story, very simple story that you evidently can sell very easily to a journalist. He will understand. An impact, tsunami, this is something that are giant, so it's always very nice to publish giant things for people. Okay, so what we did, in fact, because I was working in a university here, in fact, in that area, in Monterey, we visited all these outcrops. And what we have seen is a story which is a little bit different, and to me this is still controversial. I'm not sure, I have to be honest as a scientist, that I am fully right, but what I can tell you, it's a little bit problematic. Why? And here you will do a little bit of sedimentology. Okay, first of all, if you have a tsunami, maybe you have seen some layer of tsunami because you had a huge one some years ago. Generally, it is some kind of a blanket of mixed block, and on top very of sandstone, which are covering a complete area. Okay, it's not nothing else but a very continuous layer, which is quite chaotic. Okay, and here to the first outcrops, we were a little bit surprised to see more or less these rocks. Okay, I just explain you. This is the mouth from the maestration. So what you have, this is a deposition of sediments occurring before the impact. And here you have the nonconformity and a layer here which contains the tektite, the glass shards, the what we name impact spheral, okay? And here, for a sedimentologist, there is something very strange. First, you find the spherals in one layer here, and secondly, they are cross-bedded, and they are mixed with clasts, terrestrial plants, benthic foraminiferous from shallow platform, and they are cross-bedded. What does it mean for a sedimentologist? It means just that they are reworked. This is not the original one. It's impossible. Because if it's the original one, you will have the marley layer and just a very conformable layer of spherals. Not something like that. And after, if you take 1 or 2 hours and you walk around the outcrops, you see something which is also very puzzling if you want this as a tsunami. Here's the fact that that layer here, that one and that one, if you move to right and left of the outcrops, are thinning out and disappearing. What is this in sedimentology? When you have a valley, incised valley like that, with some sediments, and you follow your layer, you are more or less losing the layer right and left. This is a channel, okay? Channel deposits. So this is clearly an incised channel, submarine for sure, but it means that it's not really a tsunami. This is just an infill of channel. You start clearly with the tektite, which are clearly linked to the impact, but in order to get this kind of things into a channel, you need to remobilize this tektite. This is not the original one. And after on top here, what you get is this sandy limestone, and after an alternance of very fine sandstone and shale and marls, and only here you get the KT boundary with the iridium. So now you start to understand the problem. If you want to link these outcrops to an impact, one single episode, you have to say that these things here, which is Chicxulub impact, and these things, which is Chicxulub impact, Chicxulub is the name of the impact on Yucatan, well, you have to say that these things has been deposited in a few minutes as a tsunami. But it's clearly not the case for several reasons. And this is a scenario by, well, all people really believing that you have an impact almost everywhere. Impact on Yucatan within minutes, glass, melt, rocks, spherules, airborne, which is wrong. They are remobilized in a channel. And in hours, I like this hours because it's impossible to prove on outcrops. A giant tsunami wave, 1 kilometer high, wow, it's big. I have some doubt about that, but anyway, this is a nice story to sell. Causing slump and depositing massive sandstone like that one. And as a tsunami wave slash back and forth across the Gulf, you have alternating sandstone deposition with here some ripples with opposite direction following the backwash, okay? And here I asked to 4 master students. They map all the section, more than 51, all around. And what I found, there is only really 2 places where you can see ripples with that direction and straight away ripple that direction, the backward wave, if you want. The wave go through the Gulf of Mexico, is hitting the coast, and I come back, wash, and so on. And in fact, all the measurements that we have done are just giving the same direction, the direction of just a very simple channel. And we have found this kind of things in several outcrops. Another problem here, which is also, but here you have to be sedimentologist, not astrophysicist. It's a big problem. If you don't know how to look at a rock, clearly it's a little bit more complicated. That's why geologists are important anyway. This is maestration marls, and here you can see in that outcrops that the tectic layer from Chicxulub are separated by the spheral layers by a sandy limestone, which clearly has been lithified before the deposition of the second one. Cannot be a tsunami and cannot be an event of 1 minute. This is just impossible. And moreover, if you do ichnofacious, there is some in this sandstone here. We have burrows, meaning that an animal here was living on the surface, and was burrowing these rocks. Okay, it takes time also. You cannot do that in 5 minutes. Okay, so all these things point towards maybe a more difficult scenario. No, not an extraordinary scenario implying a tsunami deposition in a few minutes. This is just an incised valley. You have a sea level drop, and you have some erosion, and you infilled your valleys afterwards. The swells are linked to Chicxulub, but the rest are probably not linked to tsunami. You can find these things in several sections. It's always the same kind of distribution. You have here the marls, and afterwards you have the impact spherules, the massive sandstone, marl and shale layer, and the iridium anomaly on top. And if you follow these outcrops, you see that these are incised valley channels. You lose these rocks left and right of the outcrops. So, well, we really think that this has something to do with normal sedimentation and sea level drop. It's a more long-term deposition. But I can tell you, the first time that we were presenting this data, this was a meeting organized at the NASA in Houston, and in the room there was 300 people which were believer, to me not scientists, but believer, that impact is everywhere and indeed everything. You know, all these people are thinking that all the things that I just showed you, the Permian Triassic, the Grand Triassic, all these things are driven by impact. This is clearly not the case. And here, I would never deny the presence of an impact at the Kitty boundary. Never. My colleague Gerta Keller doesn't agree with me, but I am sure that there is an impact, maybe several, some kind of comet shower. But I think more or less the effect of this impact on the biosphere was not so big. And Deccan, as you will see, was probably a lot more detrimental than this impact on Yucatan, or this impact. Okay, so after we sent many master students to do some mapping, and we found something which is interesting, quite interesting. This is, remember, I show you the tsunami here. So the tsunami, this is this clastic bed. The swirls bed are there and there, okay? And looking at several sections, they find something very strange. The presence 9 meters below these clastic deposits and the swirls, 9 meters below, the presence of swirls bed. And these swirls bed were better preserved and not mixed with some other material like this one, which was cross-bedded at the base of this clastic deposit. This is maybe the original layer. And it would be more or less what it would mean. It would mean, because we have some dating here, we have some micropaleontologic dating. This is the last zone of the Maastrichtian, the foraminiferal zone, meaning this is something around 150,000 years before the Katy boundary. So it means that this thing is probably predating, okay? And it means that Chicxulub maybe is not of Katy age. But you have the iridium on top. So that's why we came maybe with a comet shower theory. Why? Because we have these things, Chicxulub, we have the iridium at the anomaly almost everywhere, which apparently doesn't really correspond to that, but I will tell you that this is really controversial. I may be wrong, I don't know, because there is a possibility. And also, it's quite clear that these things is predating, and we have also here another crater which postdate the Katy boundary. This is a Baltish crater, a small one in Ukraine, former Soviet Union, which clearly is younger than the Katy boundary. And you know, in Earth history, this kind of comet shower were sometimes quite common. And there is one at, for example, the Eocene-Oligocene boundary, where you have multiple spheral layers, which clearly indicate several bolides. But here's the question: is, you know, for an impact people, it would mean that maybe Chicxulub was not so efficient in terms of mass extinction. I would not say that. I would say, and you will see this with my main conclusion, okay, if you have just one impact, as these ones or this one, it's not enough to create this mass extinction. I will explain why after. If you have only volcanism from Deccan, it's maybe also not enough. Cannot explain, for example, the abrupt disappearance of the planktic foraminifera that I just showed you in the GCSP. So it's probably the conjunction of the two phenomena. This is very important here. And for this, I am typically Swiss, neutral, but I would say that the two working hypotheses are completely valid. But to me, maybe if you make some calculation, the Deccan was maybe more detrimental, but we need some work to do that. Well, here, this is controversial. Why? Because you can also do another interpretation. Because these layers here, some people will argue that these layers has been maybe slumped, reworked. Because if you have a giant wave on some soft sediment, it could be possible that part of the spherules may be deeply, more or less, embedded in this soft material. We don't really see that, but as there is not so many lateral continuity, I would say let's open this hypothesis. Just a message to bring home here is to say, okay, it's maybe a little bit complicated, it's maybe a comet shower, but doesn't mean that there was no meteorite, please. There was, for sure. Okay, and this is another view, just to show you more or less another section here with the same original layers and the reworked one. And this is always northeastern Mexico. But just to show you a picture of these spherules, these are glass spherules, okay? And if you analyze the glass here with the isotopes, for example, oxygen isotopes, you have the composition which is quite the same of all the spherules that you have all around Mexico, meaning that they have the same origin, meaning that this is origin is a Chicxulub crater. Okay, so what about the Chicxulub crater? Clearly, we published these things because, well, it's quite difficult to publish these things when 90% of the people are just believing only in impact. But at the end, it was possible, and we published one paper in geology, one paper in PNAS, and this paper we have published it in geology because here this is the crater, as you can see here, okay? And there is several cores which were almost lost. And it was really funny, one professor, a retired professor from Texas, called us and say, you know, I don't believe too much on what Walter Alvarez is doing, and I have all this core in my ground floor because I kept them because the Mexican wanted just to throw it. And if you want, you can take it. So we took it. And especially there was not all these cores. Some are published here, but these cores were new, this one also. And this central one doesn't exist anymore, and this is really a pity, because here, what you see, this is the melt rock, this is the breccia. This is the breccia. I guess you have a breccia in your impact close here. This is the same kind of breccia. I will show you a picture after. And something which is strange, a little bit like as we've seen north in Mexico, you have still some maestration here. And it's funny to think that, I think it was, yes, in the 70s, long time ago, the geologists who are in charge, more or less to describe these things, this is a report from Pemex, Petroleum from Mexico. He say, okay, here we have a melt rock, so it must be a volcano, because it doesn't really know at this time what it was. But here, clearly there is still some Cretaceous on top. And after, this is in blue here, the platform carbonate. You can see that you have a nice morphology of a crater. There is no problem here. But this is clearly a problem. And nobody were mentioning afterwards this discovery. The fact that there was some planktic foraminifera of uppermost Maastrichtian age above the breccia, which make, like I just say for noise on Mexico, it will give you an age of latest Maastrichtian for this impact. So rather controversial. The controversy was so strong that people decided to drill a big hole, because, they found the breccia at 900 meters deep, and they drilled down to 2 kilometers, more or less. What they did, in order to put end to this controversy, they say, okay, we will drill a hole in the center of the crater, and we will see what will happen. It's what they have been done. But the problem here, you know, these people were so sure that it was a huge crater. They decided, they say, okay, we'll put this in the center of the crater, and they were thinking that the crater was at least 250 kilometers in diameter. And in fact, the crater was not 250 kilometers in diameter, but 120. So they drill on the ring, not in the center, which is first a problem. So it was really quite funny to see, because you can follow more or less the drilling report on the web. And they say, okay, we cross, I don't remember exactly, 600 meters of tertiary carbonate platform that you have on top of the Cretaceous tertiary boundary. And after, what will happen? Oh, yes, we have the breccia. Good. And the breccia, it's an impact breccia. There is no doubt about that. And the breccia, you can see it. This is this suevite breccia that you have here. And after, they say, okay, we'll go on and find the melt rock, the basement, because the meteorite must have dig a big hole and vaporized all the sediments and melt the basement. And after 3 days, they say, oops, we have carbonate again. So it was very clear that there was not in the center of the crater, but on the ring. And after the ring was made, they just drill over 2 kilometers of a very nice sequence, where you can find the Cenomanian Turonian, the Aptian, all the organic rich level, a very nice conformable section that you can see. I can show you. No, I will. Oops. This section is that one here. This is Yaxcopoil. So you can see here, they found, this is normally what they wanted to find. Carbonate from the tertiary, the breccia, and the melt rocks. And here what they found, carbonate for the tertiary, and I will discuss this later, impact breccia, but here, a very nice sequence. So they were on the ring, okay? And clearly this has been a problem, and this kind of core drill were quite expensive, because you can see this is more than 1,400 meters drill, which have been, quite expensive. And here I have to say that the Mexican, which were paying part of this drill, were quite furious, because they were really asking to these guys responsible for the drill, to do seismic lines to check if they were really in the center of the crater. And they say, no, it's too expensive, we don't want to spend $500,000 in order to do seismic line. So they didn't do, and I think it was a big error. Okay, so now there is quite a controversy here again, because here you can have two interpretations. You have the breccia here, okay, and after, again, some carbonate. And these green things are glauconite. You know what is glauconite? Glauconite is green minerals. It's some kind of phyllosilicates. And yes, this formation is typically of marine origin. So glauconite is more or less forms on the seafloor when there is a very low sedimentation rate, And more or less it's a clay which is evolving into a phyllosilicate, very rich in iron and potassium. That's why this is the only minerals in a sediment that you can date with radiogenic method, argon-argon, or potassium-argon. And this glauconite indicates one thing, that it took times to form, meaning that there is a period of where the sedimentation was very slow, okay? And this you can also see here, very nice bioturbation, and you will see that the KT boundary is here. So we have again the same problem, what to do with that? And what happens here, this is just a view of the glauconite layer, the KT boundary. This is an X-ray data, and the green one is a glauconite, typical glauconite. And the EDX spectra from electronic microscopy is showing also a typical glauconite. And what is still more interesting, remember that we said that the KT boundary was characterized by drop in delta C13, and the drop in delta C13, you can see it here, no problem, is here, okay? And here, Gerta Keller found some foraminifera, and these foraminifera are menstruation. And here, again, it's a controversial. You can do two interpretations. One interpretation, you say, well, this is close to the crater, so all these things, again, here's a big waves which are reworked, but to me, as a sedimentologist, I cannot explain the presence of glauconite in a tsunami. It's a little bit difficult. People say, okay, but there is not only uppermost menstruation foraminifera here, but also some older one reworked. So typically it's something reworked. I would say that, well, this thing is quite convincing. But as I said, this is quite controversial. And to me, frankly, I stopped to work on that because I think we are losing our time. People will never agree. So you will have always some opponents. To me, I am really thinking that these are normal sediments and there is clearly a problem of dating. But anyway, you have a huge iridium anomaly at the KT boundary, so you have an impact. Point. Okay? But just to show you that when scientists are following a fixed idea, astrophysicists who want really to believe in an impact, they can take anything that they can see on the field. It will be always an explanation explaining that everything is impact or tsunami. This is a problem when you are really believer, a true believer and not a true scientist. And don't forget this. This is a very important thing. So what we have seen here, in fact, that we have some spherules apparently predating the KT boundary, while post-dating the KT, it's not a problem because these are small, tiny bubbles, more or less glass bubbles that you can rework forever. It's not really a problem post-dating. The predating is a problem. And some of the spherules that people found are not always spherules. And here I have a very nice small story that I can tell you, but it's a bit bad for the guy who published this paper in Science some times ago. And I think it's mainly problematic, let's say. I think the question is still open. But there is one thing, to be honest. We have worked very recently in small islands, which is not on that big maps, clearly, somewhere here, in front of Colombia, the Gorgoni Islands, and here the spherules bed is reworked into a turbidite, very, very nicely preserved, because turbidite will bury this glass very quickly, and the glass will be not weathered into clay minerals, because if the glass is on the ground, if you want, the weathering will transform it into clay very, very quickly. And this glass has been dated by Paul Rennie, has give a KTH, okay? There is an error bar, but if you believe that this glass belongs to Chicxulub, okay, Chicxulub, but it's at KT. But the real bar, you can always play with the real bar. I will show you that if you use argon, which is not very precise, it's not like if you use uranium lead on zircons, which is a lot more precise. So to me, it remains an open question. But anyway, this is a theory till well, the years 2000. I will show you a little bit how this theory will evolve after. It's not anymore 65.5 because you know the way to date is better and better, more precise. This is 66 million years. It's more easy to remember. A large meteorite crashed into Yucatan crater, which was quite big in diameter, causing mass extinction of dinosaurs and many other organisms. And you have the Coriolis effect, global darkness and cooling, acid rain, global wildfire, giant tsunami. Well, whatever is a comet shower, whatever it's a single impact, I am not so sure that we can explain these things by just an impact. For one reason, first of all, if you really, because you know, a lot of people have worked about the comparison of diameter of the impact and the intensity of the extinction. And here you can see, if you believe that, well, it may be right, I don't know. But if you believe that, this is a Chicxulub impact. And for me, this is a Mexican impact, which we just discussed. And for me, it's probably a little bit smaller, but let's have this size. If you want to explain more or less all the extinction that we see here, you need an impact at least of 200, 300 kilometers in diameter, which is not the case. So it means that we have to look for another killer. And here is coming India, because the other killer would be volcanism. As we have seen during all these days, 4 days already, it's clear that the volcanism is really can be really detrimental to the biosphere. It is proved at least for a lot of mass extinction. And here I just put a few things together in terms of just following more or less the history. First, what you see here, I show you that several times. You have this very nice correlation about more or less mass extinction event and the presence of this huge volcanic activity. And here, I just want to go back to some historical date, I would say. And after we'll see this in more detail. Okay, so first of all, I think this paper was very important because Courtillot and Paul Rainey show that if you date the age of the continental flood basalt or oceanic plateau, and you compare this with the age of the absolute age of extinction, you have a nice correlation. You never will have this so nice correlation with impact, never. Secondly, this was in 2003, but before there was, sorry, I am too fast. Okay. Before this date, in US, right before and after the discovery of the radium anomaly in Italy, in Gubbio, some people like MacLean was trying to show that in fact there was they could also have led to that extinction. But the career of MacLean has been completely destroyed by Alvarez, Luis. You know, when you get a Nobel Prize, you can do politically what you want and eliminate all your opponents. There is no problem. It's what he did for 10 years. I am speaking about the father, which is not anymore alive. Walter Alvarez is still alive, but he's retired, and he's not like his father, clearly not. A lot more, let's say, friendly. Okay, so here in 1990, in fact, this was interesting because a French group start and in collaboration with some Indian, like Syed, for example, start to work on the paleomagnetism. of the Deccan traps. And at the beginning, they were showing more or less, showing that, in fact, 90, for example, that at the beginning, you know, people were saying, oh, well, impact flood basalt from Deccan were lasting so long, millions and million years, it cannot really be detrimental for the KTB mass extinction. It cannot really be the case. And, well, maybe, but Courtillot in the first work show quite nicely that it was maybe less than 1 million years. And in 88, Gerta Keller show also that we have some gradual extinction starting before the KT boundary, meaning that something was behind that. But at this time, nobody really were speaking too much about the Deccan. And in 85 also, Courtillot and MacLean, the guy who cannot have any position in the university because he was blocked by the Alvarez family, was also arguing that Deccan may have been detrimental. But, well, these things well, a little bit hidden, you know, since 2005 and 2009, and here there is a very, very important work of Cheney et al., and in which Said Kadri participate a lot, showing, in fact, doing palomac, especially in the Western Ghats, where you have maximum thickness of the lava pile, and from if you go from Mumbai to the Western Ghats to Malabeshwa, you get all the Deccan formation from Java up to Malabeshwa. And doing paleomac, she showed a very nice things, in fact, that there was a main phase. I will go back to that, but there was a main phase very close to the KT boundary. Oh, by now we are stretching the period where you have the maximum eruption. Suddenly quite close, but well, this paleomac crown, you know what is paleomagnetism. Sometimes you have in white the normal the reverse polarity, and in black the normal polarity. Okay, and here the KT boundary is in the upper part of the crown 29 reverse, and this is due to more or less the paleomagnetic field, which a change of polarity following more or less the activity that you have between the nucleus, which is solid, and the mantle, which is a little bit more viscous. And in fact, you can see that she said, okay, all of this is 29R. But 29R, duration, cross the KT boundary, but the duration is still quite long, more than 700,000 years. And she said also that there was some phase, but I will go back to that later on. In 2008 and 9, this is where we start to work. And my first time in India, first was a meeting in China, but in 2002, organized by one of the best micropaleontologists that India have, because he's still alive. This is Dr. Govindan from working mainly on GC. And he say, okay, you have to go in India because in between the traps, we have some foramnifera maybe. And after we conduct in 2000, I think it was 3 or 4, some research in Rajamundry. I will show you this research with a group mainly of French and also Sunil Bajpai from India. And we sample all these things, and we think effectively that we have a good idea about the timing of the extinction of foramnifera compared to this emission. But Rajamundry is quite special. I will tell you why after. And after we went with people like Bandana Samant, Moabi, Sunil Bajpai to Jilmili, which is close to Nagpur, not so far from here. And in Jilmili it's quite interesting because there is a very thin layer which is full of planktic foramnifera. We'll go back to that also later on this afternoon. But this is really interesting because it's a way to date. And after we publish all these things, and in 2014, we also published a nice paper. Thanks to ONGC, we got the access to ONGC cores in the Krishna Godavari Basin. And here in the deep section, where the lava flow are ending into the sea, you have a lot of intercalation of marine sediments, where we found quite a lot of planktic foraminifera. But I can tell you, to deal with ONGC people takes some time. If I remember, we started a discussion some years ago. I probably drink 1,000 liters of tea with them, discussing. And the problems with ONGC, they are very nice people. It's not a problem. Smiling, friendly. But the big chief is changing every 2 or 3 years. So every 2 or 3 years, you have to renew the discussion and to start again from the beginning up to the top. And sometimes it's a little bit tiring. But at the end, we had more or less a chance to have access to the store in Rajamundry and to sample these things. And by this way, I will show data later on. And know what next? Okay, what next? This is the dating that we had, that we obtained, a very nice dating that we obtained later on. Okay, so just a comparison, because we know since quite a long time, because there is also a lot of people that I don't forget from England, which I work on Deccan, Self, Widdowson, Bean. A lot of people have worked also. And especially we were more volcanologists, so more interested in some calculation of gas emission, for example. And here, this is these numbers are taken from given to me by Vincent Courtillo. And here you can see, I don't want to go into detail about all these numbers, but you can see that if you take 1 decan megaflow, it's a lot of this sulfur dioxide. And if you just think that the whole decan traps is probably on the order of more than 100 impact, okay, in terms of sulfur dioxide. And we can also talk about CO2. And also all these very poisonous elements that you can eject into the sky. But the problem here, that's very nice to have all these numbers. But what you need, this is the timing and tempo. And this is here that the story is very interesting. The question here, I already show you that pictures. Here's, we know that you have sulfuric aerosol formed by reaction of salt into the atmosphere vapor, which really can after provoke acidification. We know that this is a short term because sulfur dioxide is residence time is very short. So if you have a huge emission, a huge flow, it means that you will have 1, 2 year, 3 year of cooling, but you not necessarily will see in the sediment record because this is really short. But this has a short term. On the long term, all these things will produce a lot of CO2. That's why you can get some warming event. But this is the kind of things that we need some number. But in order to get number, to get the emission rate, you need some timing and you need some absolute date. And it's what we have done. But I will first start from the beginning of the story. Okay, because you already have seen that clearly Deccan activity may cause an important increase in CO2, 3 times than actually, probably. This is some kind of calculation, but less than 3 times by now, unfortunately. And this lead to a warming, which was quite abrupt, general warming. I will show you that later on. But short cooling intervals that you necessarily not see necessarily into the sediments because these are too short period. And interestingly, this could lead to social acidification, a carbonate crisis, and some planktic foraminifera extinction, for example. But this also may lead to weathering and this will decrease the CO2. Just only, for example, the weathering or all the decant traps may decrease the CO2, and you increase the nutrients and you help to the recovery. But this decrease in CO2 may also slow down the recovery, so it's maybe a little bit more complicated. But mainly this is this kind of cascade events that you can wait for. So here, this is a little bit more applied to what you have into the sea. So in the stratosphere, you have this sulfate aerosol, which will absorb some light for the moment. So you get some short global cooling, for sure. But you get a lot of acid rain. And this acid rain will provoke an acidification, a carbon crisis, and you may have had a severe, very severe biotic stress. The question is when and how fast. And for that, you really need a good dating. And I show you that again already. Here you can see that most mass extinction appears to be linked with ocean acidification, and the KT boundary is here, but you can see that this is postulated for the Permian, for the Triassic, and for the PTM that we will see later on this afternoon or tomorrow morning. Okay, so what about so now, yes, I will stop in 15 minutes. Now, what we can also try to see if in the sediment record, and we work quite a lot, do we see a change? Do we see a warming? And here there is several interesting things that you see just before the KT boundary, which is quite interesting. And for example, here, these are planktic foraminifera. This is IODP core, so taken is a deep ocean. And here you see that there is different species of foraminifera, and which sometimes are, for example, for that one, are decreasing quite a lot close to the boundary, here and here. So you can make some ranking depth, but especially you can measure stable isotope, oxygen stable isotopes on benthic and on planktic foraminifera. And here what you see, it's a very interesting point. What you see is that, well, first of all, let's say something like few millions before, well into the Campanian, you have a cooling period, okay? And the early late Maastrichtian interval, it's 2 or 3 million years before, is marked by a cooling. This is very important in order to understand the mass extinction, because you know, it's to know exactly what happens before. It's sometimes more important to know what happens during this the mass extinction interval. And here, what you can see is that you have to think. You remember, we have seen the Cretaceous yesterday. Everything is linked during this course. You have seen the Cretaceous. And remember, there was anoxic black shale, a huge volcanics. It was warm, warm, and warm. Generally, overall, very, very warm. A lot warmer, a lot more CO2 than even actually, okay? And suddenly, at the end of the Maastrichtian, let's say the end of the Cretaceous, you have a cool period here, arriving. And here, this corresponds to a drop in diversity of several groups, a stress. Do you remember I show you the ridist colony? These are these huge bivalve, big ones, forming colony like the corals. And when they got this cooling, there is a drastic reduction of the species to 1 or 2, okay? So clearly they got almost extinct well before KT boundary. We can say, I will show you that later, but the dinosaur diversity also was suffering quite a lot of this cooling. So, and ammonite also were also declining well before, okay? And this is really an important point here, because it means that you have an addition of stress, okay, which start 2 or 3 millions before the KPG boundary. And this cooling is linked to the presence of ice caps on Antarctica, which is a continent, so it's easy to put ice on Antarctica if you have a cooling, a lot more easy from the North Pole, which is not a continent. And this will provoke a complete reorganization of the paleoceanographic currents. Your sea is a lot more dynamic, and well, it means that you change a lot of things here, okay? And these animals, which were more or less linked to warm, sluggish ocean, and so on, have some difficulties: the redists, the ammonites, the inosarmids, and the dinosaur on land, clearly. And the diversity is more or less going down. But you know, as I said, for the dinosaur, it's sometimes difficult to speak about diversity because record is quite poor. There is no dinosaur specialist in the room. It's okay. And after, slightly before the KT boundary, when I say slightly before, it's something like 250,000, 300,000 years before the KT boundary, you have sudden, quite sudden cooling here, followed by warming. And this we think that this is the Deccan. We were thinking, but we had no proof till this point, okay? We know that something is really happening. And during this time, for example, you increase the stress of the foraminifera. It doesn't mean that you have a massive extinction, not at all. It means that, in fact, you gradually eliminate, especially all the specialized form, which were trying more or less to adapt to cool, and now it's against warm, okay? And it's against also quite rich in nutrients. And what you get generally during the evolution, at least in the planktic foraminifera, this kind of nice change. If you increase the stress to catastrophic stress, you observed really Lilliput effect. It means that the species are more and more small. This is because probably two reasons. They are slowing the metabolism in order to survive, so they are more or less therefore smaller. And also, if the medium, if the environment is more and more acidic, as you will see, it's clear that they are generally producing very thin, fragile, and small shells, okay? So meaning that this is a direct measurements of the acidification of the ocean. And clearly in the optimum you have a lot of species, and here just a few species which will survive, okay? And Gerta Keller and several of PhD students did a lot, all around the world did a lot of studies, and show clearly one thing which is very nice. You have, this is warming of the Deccan, okay? The KT boundary will be on top here, and you have dwarf species which are clearly appearing, and let's say opportunistic species which are more and more abundant during this time. So it means that you increase the stress on the biosphere. And my colleague, Nicolas Thibault, is a nanofossil specialist. So this is a phytoplankton, okay, algae. And here he used exactly the same record than the one that I showed, the stable isotopes. This is a 525A site, South Atlantic. And again, you can see this is the period where you have the warming marked by a pronounced negative shift of stable isotopes here in both benthic, but especially benthic and planktic foraminifera. And this is more or less what you get from the nanofossils, the small microscopic remain of algae. And here you can see that there is two important things. First, the dwarfing, like for the foraminifera, which is interesting. Exactly the same that he observed with the foraminifera of Gerta Keller. And here, the appearance of Micula murus, which suggests a warming and lower surface water productivity. And Micula murus, really, it's an acme. It's really a huge increase. So it means that this species really like it warm, but Miculamurus is a species which is quite thick, robust. So if the acidification is coming, you will always find it because it's less prone to dissolution linked to acidification. And what also it shows you nicely that at the end here, close to the KT boundary, you have also a short cooling period where different species which are more adapted to cool period were appearing. Here, part of the record is missing. The last 50,000 years are missing. It would be another warmer. But there is a very nice things here that you can compare this marine record with the continental record. Meaning here, this is a very nice paper published by Wilf in 2003 in PNAS. And what they do is using more or less the leaf margin analysis. It's a paleobotanist, if you want. And of the terrestrial plant. I don't really know exactly what is the method that they use, but apparently it's quite well known that if you increase the temperature, you change the morphology of the leaf, especially the leaf margin. And you can estimate, this is based on actual work, more or less temperature. And you can see here, again, exactly the same thing. Some warming, cooling, and maybe here a warming, meaning that this warming is probably missing here. But I will show you after that we found it in somewhere else. Though it's really nice because here, this is a work which correlate the event from marine to continental. And again, you can see that it was, again, we can record this warm event that without really knowing, we were correlating with the Deccan activity because we don't know why at this period the dating was not so precise. We had another proof in the marine sediments that Deccan was acting before the KT boundary. These are the osmium isotopes. I don't want to go into details about the osmium isotopes, but generally it works like that. Well, you have, let's say, more positive values when the osmium isotopes is coming from the weathering of the crust, let's say superficial crust, like the granite, metamorphic sediments. These are more or less a ratio. And generally here, if you decrease that, it means that you have either the weathering of a huge basalt area, or you can explain that also by the fact that if you produce a lot of basalt on the Indian Craton, you will cover the granite and you will shut down the source of more positive osmium values, which is also an explanation. And here you can see very nicely that in the last zone of maestration, corresponding to the warming I just showed you, you have effectively some kind of an acceleration, and we link this to the Deccan pulse. The most negative here, the most the most negative things that you have here, these points are probably linked to the meteorite because osmium ratio is more negative in the meteorite. So you have probably these two things, but it's a very, very interesting record that show that something was acting just before the KT boundary. And when I say just before, it looks 200,000 years before the KPG. Okay, another things also, and after I will probably let you have some lunch. Okay, no, we will stop here, I think. Okay, we are starting again in 1 hour. Okay, good.